Then you can go back too.
This is
if you need to go back.
Okay. Hi, everyone. I'm Xiaozhen. I'm a research scientist at Facebook. I'm here today to talk about how we automate and scale our edge network. This is the agenda of my talk today. First, I will give an overview of Facebook edge network. Next, I will talk about how we manage our network, which we use Robotron, our automatic network management system. Then, I will talk how we use Robotron to scale our edge network in a fast, smooth, and incremental way. And finally, I will share some takeaways. So what's the scale of Facebook community? We have millions to billions of users actively in our family of products, from Facebook to WhatsApp to Instagram and Messenger. So how we deliver content reliably and fast for such a large user community? Through our high-performance network infrastructure. Facebook network consists of three major components: edge, backbone, and data center. They are all globally distributed around the world. So when a user visits our service, the request is first routed to the nearest edge network point. If it can serve the request, a response will be returned right away. Otherwise, the request will be forwarded through our backbone to a data center. The data center processes the request and generates a response back to the user. So today, I will talk about our edge network. If you don't live on the edge, you will never see the view. Edge network is the direct connection between Facebook and our users. So let's take a look at what view users can see through our edge network. Facebook Live Video. Since our rollout of Facebook Live last year, we've been surprised and delighted to see how people use it to interact and connect with each other all around the world. From Mark's Q&A with astronauts on space station, celebrities engaging with fans, to people sharing important life moments with friends and families all around the world. Facebook Live has opened a completely new way and much more convenient way people can create, share, and deliver content. So what does that mean to our network? It means huge amount of traffic with exponential growth. Looking back, our edge equals traffic grows whenever we introduce new content type, from text, image, to video and live video. Looking forward, as we're introducing AR camera platform, social VR, virtual reality, we expect our traffic to grow exponentially. So how our edge network supports such traffic growth? It needs to scale. We scale our edge network in two dimensions, topology and hardware. For topology, we go from small size to big size, one type to multiple diverse types, simple design to complex multi-layer design. For hardware, we also go from using one vendor across all our edge networks to using multiple vendors. And we upgrade our network speed from traditional slow 10 gig to global high 100 gig. So how we do it? To ensure smooth and fast scaling, we follow a few principles. First, upgrade only when there's traffic demand. So we do not over-provision or over-complicate our network. Second, upgrade incrementally, modularly, instead of a monolithic full redeployment. This is due to space and power limitations in our edge network size. And third, upgrade without affecting existing traffic, so our users are not affected by this upgrade. And finally, upgrade fast and automatically, so we can roll out our new content type like Facebook Live globally as fast as we can. So how we do it? Take a simple edge cluster topology as an example. The cluster has 4 switches and a rack of servers caching content. It connects to the backbone, our own backbone network, and the internet through a small number of peering routers, for example, 2 routers. Before, we used to have such small, simple, and unified topology across all our edge networks. Now, with different regions, seeing different traffic growth, therefore, needs to upgrade to different topology and hardware. Let's see how we can do it incrementally. So if some region only see a small traffic growth, then we simply add a few racks to the cluster. If existing links cannot support traffic growth, then we can add more links. Further, if existing device hardware that cannot support this many links, then we can upgrade to more powerful vendors, device that could be from a different vendor. And if adding more links does not help, then we can upgrade our links from traditional slow 10 gig to high 100 gig. For redundancy and capacity requirement, we can also add more routers. And if in some region, the traffic really grows, requiring our edge network to process a lot of video content, then we can add more complicated router layers that can provide more powerful computing and routing capability. And with our upgraded routers, if one cluster cannot cache enough content, then we can add more clusters. And even more aggressively, if we upgrade our cluster switch as well, then we can connect our clusters to switches directly. And then there will be a scale of a lot of more clusters. So with so many different upgrade options and different regions has to upgrade into different topology and hardware depending on its user popularity and its content sharing pattern. How we do all of this complicated global edge network upgrade fast and smoothly? Of course, human manual upgrade is impossible because it's inefficient, unscalable, and error-prone. We have to do it automatically. Thus, we use Robotron, our automatic network management system. Robotron replaces tedious human manual effort into a robot-like system that makes managing our network cost-effective, reliable, and scalable. So next, I will describe Robotron, our automatic network management system. The foundation of Robotron is a vendor-agnostic object store. We call it AppNet. On top of AppNet, various management stages are built, from high-level network design to low-level vendor-specific config generation, to deployment of these configs to devices, and continued monitoring of our network devices. We have a paper, second paper last year, describing more details of our Robotron management system. So let's first look at how AppNet models our network. I will continue to use this traditional 4-post edge cluster as an example. So the cluster has 4 peering switches. We call it PSW. They connect downstream to the rack switches and servers, and upstream to peering routers. We call it PR. Each PSW has a 10 gig link to each PR. So let's zoom into the link between a PSW and a PR. The link connects physical interfaces, ET11 and ET21 on PSW and PR. And they are aggregated logically into aggregate interface. The physical interfaces live on line card. A BGP session is established between the IPs configured on these aggregated interfaces. So consider the part of the link circled red. These network components are modeled as several AppNet objects. a network switch object, a line card object, a physical interface and aggregate interface object, a V6 prefix, a BGP session, and a circuit object. Object can have value fields like string or numeric value. For example, physical interface has name ET11. Object can also have relationship field. For example, a network switch is related to line card. A line card is related to physical interface, etc. So the complete relationship looks like this. Consider this only captures half of the link. You can imagine how complicated it is to model the entire Facebook network. This model snippet shows part of the definition of our circuit and physical interface model. You can see that models are related to each other. For example, circuit model is related to physical interface model. And physical interface model is related to line card, aggregate interface, and device model. So with IPNet modeling our network as a foundation, we build 4 management stages: network design, config generation, deployment, and monitoring. Let's first take a look at our first 2 stages. Network design and the config generation, they are intent-driven. Network design translates high-level human-expressed design intent into concrete IPNet object. Then config generation generate device configs based on this IPNet object. For example, a design intent could be build a cluster with 4 switches, 2 routers, and 2 racks. And then they are translated into hundreds of IPNet objects, which is then translated into tens of device configs. Let's first take a look at our network design. Given a design intent, Robotron used a template to capture devices and the links specifications for this topology. In this example, it specifies 2 PRs, 4 PSWs, and 2 top-of-rack switches, and with their corresponding hardware specification, like router, switch, different device role, and their vendor. It also specifies the link groups between different device pairs. In this example, there's link between PR to PSW and link between PSW to top-of-rack switch. Based on this template, Robotron validated it against the IPNet data and then generate corresponding IPNet object. For example, based on this template, it generates 6 network switch objects, 2 network router, 16 circuits, and dozens of physical interface, aggregate interface, prefix, and BGP session. For this particular example, it generates hundreds of objects across tens of models with more than 100 relationship fields. So based on this IPNet object, config generation generates vendor-specific device configs. It feeds this IPNet object to a vendor-agnostic config scheme. The config scheme will capture the variables that will be used to generate configs. For example, a device has a list of aggregate interface. Aggregate interface will need name, number, prefix, a physical interface to generate a config, and physical interface also need a name. This vendor-agnostic config scheme is then combined with a vendor-specific config template to generate vendor-specific configs. Here, for example, we have different vendors. Each vendor have their own template, interface, BGP, MPLs. This, I show an example of an interface config template from a specific vendor. We capture static content as plain text, and then dynamic variables and control flow using the template syntax. So based on this template, we can generate massive vendor-specific device configs and push them to devices. So I will skip deployment for the interest of time, and then mention monitoring briefly. So our monitoring, to ensure our devices are running normally, we use various collectors like CLI, SNMP, RPC collector, even our own Thrift collector to collect devices, vendor-specific data from the devices directly. This data is then normalized to be vendor agnostic. And then this data, vendor agnostic data, is fed to our downstream system like visualization, storage, alert, etc. So this is how our management system, Robotron, manages our network. Robotron was started in 2008. And since then, it has been used to manage and scale our entire Facebook network, not just edge. It also used to scale data center and backbone. So today, I will describe how we use Robotron to scale our edge network. Remember, our edge network needs to have new topology, new hardware, new vendor. All of this will need to us to change our existing system a little bit. For example, we add new model in AppNet to model a new topology, new device, new circuit, new device role. We add new network design for the new topology, new config template for new vendor, new deployment workflow if the vendor support a different workflow, and then new collector if existing collector is not sufficient to collect all the existing data. The principle we follow is we still try to leverage existing Robotron system so that our users, when using Robotron system, they see minimum change. They can easily adapt to the new upgrade to new topology. And we change our existing system only when necessary. So first, AppNet model change. For topologies and hardwares that is already modeled in AppNet, for example, this network device, it has chassis model, line cards, device role. Then we try to use existing model. And we only add new object that capture new chassis, line card, or device role. For topology and hardware that is not modeled in our AppNet, for example, to support multiple speed in our circuit, we add this new field, speed, to our circuit. So we can create different circuit object with different speed, like 10 gig, 40 gig, 100 gig, etc. So with AppNet model being done, next, we need to change network design to support new topology. Remember, network design translates high-level design intent to concrete AppNet object using a template that captures the device specification and link specification. Now, if we want to add more racks, we have to model this variable. Then we increase the number of which we make this variable. We make this number of devices a parameter and a variable. And then we need to add this to the template. And further, if we want to increase the number of links for capacity, then we add this PIFs per AGG, this parameter in our template, and then support this. So users can choose different number of links in different regions, depending on the traffic growth. And further, if we want to use different vendors for our devices, we leverage existing hardware. Like we specify the device role, router switch, and the different vendor role. But we have to validate all of this new device role, new vendor role against our AppNet model. For speed upgrade, 10 gig to 100 gig, again, we have to model this speed, make it a variable in our template so that users can specify whether they want to use 10 gig, 40 gig, 100 gig, or even 200 gig in our template. And finally, to add more routers, we can leverage existing parameter, like change the number of devices in our template. Now, to add more router layers, this does need some work. Like we have to support new device role, like PR1, PR2, with new device specification, a different device role, different vendor. And we also need to add link group corresponding for the new device links. For example, PR1 to PR and PR2 to PR. And finally, to add a new cluster to our existing topology, we need to add a new template for the new cluster. Remember, all of this looks simple from the user perspective. So we try to minimize our template change, and then our users can use our template to adapt and upgrade to more complicated and different topologies easily. And we move all the complicated device and link specification, like add new device role, validate new device vendor, validate new hardware, and all the port map allocation rule, prefix allocation rule, circuit allocation rule to the backend. So our user is not affected too much, and they don't need to adapt to a new, different system. So this is how network design change need to be done. With network design change need to be done, then we need to move to config generation stage. Remember, config generation they feed the APINet object to vendor-agnostic config scheme, and then combine with vendor-specific config template to generate device configs. Now, if we have to use devices from different vendors, then we need to add more config template for the corresponding vendor, and then generate device config accordingly. Finally, for monitoring, remember, we use various collectors that collect vendor-specific data and then normalize to our system. Now, for new vendor, if it supports existing collector, then we just send it using the existing collector and then feed to our system. However, if the new vendor requires a new collector that we haven't implemented before, then we have to add a new collector. Once we have that, we feed all of this vendor-specific data still to our normalization system and feed to the downstream system. So there's no change needed for the downstream system, like visualization, storage, alert, for adding a new vendor or new hardware. So this is how we adapt Robotron to scale our edge network. We try to keep existing system with minimum change, and then add new changes only necessary, like add new model, new design, new config template, new deployment, and new collector. Okay, so finally, I will share some experiences and takeaway we learn from this process. First of all, our network is constantly scaling for our new product and high traffic demands. Our network management system needs to always be flexible and scalable, extensible to support such network upgrade. For example, support new topology and new hardware, support incremental upgrade, not affect existing traffic, and do it fast automatically. And if we have such a flexible enough system, then it can significantly improve our network upgrade efficiency. For example, Robotron enabled our global edge site upgrade to multiple heterogeneous topologies, vendors, and hardwares in only a few months, 3 to 4 months, with a handful of engineers, only 10 to 20 engineers, while constantly making sure the existing site serving user traffic and without causing any problems. So that's all. Thank you, and I would like to take questions.
Okay, the question in the back left there.
Yeah, thanks for a wonderful presentation. One question I have is, how can you test this kind of management system, especially at scale?
So the question is, how can we test all of this upgrade as we do this in scale? Definitely, we have multiple testing systems in both software and hardware, and also we have a lab. So first of all, we have a sandbox testing, a whole testing system. Whenever we add a new topology, new hardware, new vendor, new device role, new circuit role, all of this new port map allocation rule, we run extensive software testing to make sure it at least first pass our software. And then we have a lab environment. We test some new topology, of course, limited new topology in our lab deployment, in our lab environment by deploying the real new device, real new topology, and then use our software to test it. And finally, once we pass the software testing, the lab testing, then we roll out it globally. But we roll out this phase by phase. Like I said before, we roll out all of this global upgrade incrementally, site by site, so we don't mess up the whole network.
So can I assume you're testing in this phased-off fashion? So each phase,
Yes.
you're treating it as a test steps. If it fails, you roll back.
Yes, yeah, we can easily roll out our the new software or the new testing. Yes.
So in the history, there are simulation approach which can provide kind of testing for the large-scale networks. Have you ever thought about this approach?
Yeah, we do have a few. Yeah, we have, like I said previously, we test all of this in our software. There we have a different simulation, emulation system, so that we just take all the global topology into our system, like, okay, router, switch, rack, server, and then we simulate all different failures. We try to make our system as complete as possible to capture the whole kind of different failure scenario. But there are some cases that we cannot really test. For example, when we do real deployment, there's some problem with optic, with hardware, with whatever vendorship. That we have to test that in the lab. That's the second phase. And then again, yeah. And then when we do real deployment, we also see real problem that we haven't seen before in our software or in our lab. That we need to do that carefully. That's why we do this incremental upgrade side by side. So we minimize the affection as much as possible.
Sorry. So you mentioned the compilation process from the templates to the device configs. So I was wondering, I mean, you mentioned your SIGCOMM paper too, and there have been a lot of papers recently that describe a slightly high-level abstraction where you could make the properties that you need from the configs be part of the spec itself. For example, if you wanted loop freedom, or if you wanted to avoid black holes, or if you wanted path redundancy for fault tolerance. All of these could be made part of the spec along with the topology template. And your compiler makes sure that all of these properties are ensured when the device configs are generated. Have you thought of anything on these lines yet?
Yeah, we do have some validation when we convert, when we do the network design and config generation. Like the network design has a template, specified device specification and link specification. There in the backend, so for the user, it's very simple, only in device and link. In the backend, we have various different validations to make sure, for example, some vendor can only have some limited chassis model line card, and the circuit must have AZ endpoint. Prefix must be associated with aggregated interface or physical interface. BGP session must have AZ must have prefix. So we hide all of this complicated validation logic in the backend. But yes, we do have all of this. The same thing for config generation. When we generate configs, we validate, make sure the config syntax is compliance with whatever vendor specific to us. So we try to minimize the problem when we do the real config push or when we do the real deployment.
Yeah. So I've seen you guys use the Robotron for design, deployment, and monitoring. So is it also covers the operational changes, or is that also being generated as a config push and then being pushed to the devices?
Yes, so the question is, Robotron do design, config, deployment, monitoring. The config push part is the deployment, so I didn't talk about it for interest of time. But yes, Robotron also includes the massive push of configs to tens, hundreds, thousands of devices in parallel way. And there we do dry run, we do different validation during device push, like dry run, no dry run, and then push to a small group of devices first, and then monitor a little bit, and then push to a large group of devices. Yes, Robotron does include that phase.
So do you guys use any like a CMDB kind of a thing which has the data for all the variables?
Sorry, could you repeat your question?
No, is there any configuration management database where you store the values for all the variables, what you're going to pull?
So the variables of the, yes, yeah. First of all, the raw network data is stored in AppNet. And then the AppNet data is fed to the config generation stage, and then generate device. So yes, there are intermediate stage that we also store the variables that are used to generate config. And then for real device config, yes, we also back up real device config. In case the new generated config is inconsistent or is wrong, then we can quickly roll back to the previous golden, we call it golden config.
Okay, thank you.
Yeah.
In how many countries do you
Sorry, where is the question?
in how many countries do you have the edge network?
I cannot reveal the I cannot reveal the exact number. I would say a lot of configs, maybe I don't know, hundreds of thousands of config. But first of all, I didn't calculate exact number of config, but yes, there are a lot of config. First of all, for every single device, there's config. Even for that single device, we back up different fees config. So yes, so there are multiple config even for a single device. We continuously back up our config. We call golden config for config validation. Yes, so there are a lot of config.
Hi. So to hide vendor semantics, we had to build a lot of tooling to separate service definition from what the service is. In 2017, most vendors will give you full programmatic access and ability to configure devices throughout programmatic interfaces rather than pushing down CLI. Do you feel we are ready to abandon CLI? Do you have any time frame in mind?
So the question is, are we, sorry, could you repeat your question?
So you're still auto-generating configs which are CLI, they are text files you're pushing down, right?
So the whole system is like just one step. Every single stage, they connect with each other. Like user can just press one button, and then we would auto-generate the topology, generate config, and then push it, and then do monitoring. But yes, there are. So we have this one button process, as well as every single stage. They can also choose only do this single stage. For example, they only generate configuration without pushing. And then they can choose, okay, 1 day later or 2 days later, they press a button again and then push config. Yes, that we do have CLI tool, we have visualization tool, we have different tools to enable that function.
Do you feel you're getting enough support from your vendors to abandon pushing text files down and use programmatic interface to configure them?
Oh, that depends on whether the vendor support it. Like we've heard of like OpenConfig, they are working on like providing vendors support the JSON instead of plain text. If the vendor support it, then yes, we will consider that. So again, depends on whether device support it.
Thank you.
No.
To develop something called OpenConfig.
Yeah.
So which defines a modeling language. So how close is your data modeling? How similar or different is your data modeling with OpenConfig?
So I would say they are different because our Robotron started in 2008. At that time, maybe OpenConfig is not mature yet. So yeah, but we are actively looking at OpenConfig, the YAN model, how it model the device and the config compared to our model. And we are actually looking at how much effort and whether we can migrate our config generation the stage to using OpenConfig. It's an in-process effort. So yes, we are actively looking at it. But there are like Windows, like OpenConfig cannot capture the whole thing. For example, as far as I know, it cannot generate the QoS config. So we will still have to have some of our own config generation pipeline while adapting OpenConfig. So yeah, so that's the current status.
The very back?
Yeah.
Yeah, great.
So does monitoring help in auto-correcting the configuration if in any case like the intent and the actual deployment is different due to maybe like manual errors or like somebody like
Yes, it could happen. Like if the users, if they want, okay, 2 router, 4 switch, but then they specify in the template 1 router, 4 switch, then we will generate config based on whatever intent, only 1 router, 4 switch. And then we've got this requirement from our network engineer. They say, okay, if they only have a limited number of specifications like topology, now we add another layer of validation saying, okay, there's only this limited number of values you can choose from the topology. So you cannot put, for example, 100 router. You cannot put a large number of something that is unreal in our topology template. So that's part of our topology validation.
Okay. So does that mean that the monitoring phase continuously validates the intent?
The monitoring continues, yes, yes. Actually, in our system, like what I talked today, the design, it's a desired database model. So our AppNet, we have different database model. Desired, which is the high-level intent, and we have a derived model, that's raw data we discovered from the network. And then we compare desired versus derived and see what's the difference between the two. That can show some discrepancy between desired and derived. But that can also be indicated like, okay, we plan the network like half a year ahead of time. So there will be such discrepancy. Again, we will need to add software to distinguish these two discrepancies, whether it's really because, okay, the network is wrong, which is different from desired, or it is because the desired is ahead of derived for future provision, for future prediction. So yes.
This is really inspiring. Thank you so much for sharing. And you mentioned that your Robotron can work not only for the edge network, but also a backbone as well as data center.
Yeah.
My question is, do you have any plan to use Robotron for backbone as well as data center in Facebook? If not, it would be great if you can share if you have any challenge to do that.
Well, yeah, that will be another 25-minute talk. How we scale backbone, how we scale data center. Yes, definitely. Robotron has been used since 2008, and it is the single network it is the network managed system we use to manage all our network. So yes, like for example. What Henry talked about, like our Express backbone, right? They also based on the same Robotron system to build a new Express backbone at Facebook. And then for data center, yes, we've gone through different scaling stages, like building multiple cluster, building aggregation layer on top of this. We all use AppNet as a foundation and then different management space of Robotron. So yes, we do use Robotron. And if you want to know the detail, maybe next time I can talk about how we scale backbone, how we scale data center.
All right, please help me thank Xiaozhang.
Thank you.
Thank you. All right. Awesome. Thanks.